In this video, we will look at working with flow entries on OpenVSwitch. I'll demonstrate using the OVS kettle command to manually add flow entries to OVS. Flow entries on an OpenFlow capable switch like OVS control the behavior of packets arriving at that switch. Flow entries would usually be installed dynamically using an SDN controller. However, installing them manually greatly helps us understand the concepts of flow entries. Everything I cover here is found in the OVS kettle man page, which can also be found at openvswitch.org in their documentation section. If you're not already familiar with OpenVSwitch, OpenFlow, or Mininet, I'll link to the source organization's websites for much more information. Also, you can watch my introduction videos to all three topics on my YouTube channel. I'll use Mininet to emulate a simple network with one OVS switch as well as 3 emulated hosts. The hosts will be H1 through H3. The name of the switch is S1 and it has ports S1, ETH1, ETH2, and ETH3. Something very important here is that although our system sees these port names, we need to know how these port names map to OpenFlow port numbers, which in this diagram can be seen are OpenFlow ports 1, 2, and 3. In a moment, I'll show a way to check this mapping. Here I'm running Mininet in a virtual machine downloaded from mininet.org, and I'm running the VM in VirtualBox for my hypervisor. I'll launch the topology just shown with sudo mn --topo equals single, 3 -- controller equals none -- mac. The controller equals none option is there because I don't want Mininet to use the default controller, since I'll be adding flow entries manually, not with the help of an SDN controller. Also, I use the MAC option. This gives me easy to read MAC addresses, which you'll see later. Let's check our topology. Dump, and I see the nodes, as expected. Net, and I see the links between the nodes are as expected from the diagram. As I noted before, we will need to know how these ports S1, ETH1, ETH2, and ETH3 map to OpenFlow port numbers. OVS OFCTL show S1 shows me these mappings. By the way, in this video, you'll see me use sh from the Mininet prompt a lot. This is for commands that need to be run from the system shell, not from the Mininet prompt. sh lets me avoid flipping back and forth between the system shell and the Mininet prompt. Normal action flow entry. So let's add our first flow entry. In this first example, I have not specified any match conditions. I only provided an action. This means we will match every packet. The action I specified, the normal action, means traditional L2 switch behavior. So all I'm doing here is telling switch S1 to just do normal L2 switch forwarding. Let's test this out with ping all. This looks good. All 3 hosts can reach one another. Let's ask switch S1 to tell us all of its flow entries with sh ovs kettle dump flows S1. Here's the single flow entry, and we can see 24 packets covering 1680 bytes have hit this rule. We also see how long this flow entry has been in the table, 31 seconds, and how long it's been since a packet has actually hit this rule, which is the idle age, 7 seconds here. Now I'll delete this entry with ovs kettle del-flows S1. This command means to delete all flow entries on S1. Here there's just one, but keep in mind this command deletes all of them. If we do dump flows again, we see there are no longer any flow entries. Ping all, and we see we no longer have connectivity since there are no rules remaining. Here's H1 timing out and H2 timing out. Layer 1 matching. Now let's do some actual matching. I'll start with the layer 1 match and just say anything that arrives at OpenFlow port 1, send that out OpenFlow port 2. Also the reverse. Anything in port 2, send to port 1. Back to the Mininet prompt, I'll add 2 flow entries now. So anything in port 1 goes to port 2, anything in port 2 goes to port 1. I match on ingress ports with in_port. I specify an output port, or ports, with output, a colon, and the output ports. So let's check this. H1 ping, I'll do a count of 2, H2, and we see H1 and H2 can reach each other. However, note I didn't put in any rules for port 3, where H3 is uplink. So if I tried to ping from H3 to H2, we can see this timeout. Let's do dump flows again, OVS kettle dump flows S1. And we can see our 2 flows, and they both have hits to them. On these 2 flows, I defined a priority of 500. Priority is a critical concept. If a packet arrives at an OpenFlow switch and I have 20 flow entries that all match that packet, only the flow entry with the highest priority will be used. All others will be ignored. If you are familiar with traditional switch ACLs, this is the same idea, where the first match is acted on and all other matches later in ACL would be ignored. Let's quickly test this priority concept with a new flow entry. This flow entry has a higher priority, 32,768. That happens to be the default priority when you don't specify one. The action here is to drop. Also, there are no match conditions listed, which means this rule will match every packet. H1 ping H2 again. So when we tried to ping, we can see I've cut off my connection between H1 and H2. If we do a dump flows again, we'll see the new drop rule getting hits and preventing any connectivity. Also look how priority isn't listed for that rule. That's because it has the default priority of 32,768. Priorities can range from 0 to 65,535. Now let's remove only that wildcard flow. So I'll do the OVS OF kettle DEL flows S1, but now I'm using the -- strict option. That says to only remove that one wildcard flow. Dump flows again and we see the drop rule is gone while the original flows remain. And if we try to ping again, we'll see that we have connectivity once more. Layer 2 matching. Now let's do a layer 2 match. If you recall, when I launched Mininet, I used the -- MAC option. That's why I have these easy to read MAC addresses here. For my flow entries, I'll say anything from the MAC address of H1 to the MAC address of H2 should go out port 2. Also the reverse. Anything from the MAC of H2 to the MAC of H1 should go out OpenFlow port 1. Let's add these flow entries. That got cut off a little at the end there, but DL_source and DL_destination are used to match on layer 2, so in this case to match on source and destination MAC addresses. So these rules cover the behavior just described. The first rule from H1 to H2's MAC we see we send output to 2, and from H2 to H1's MAC output to port 1. So I have my layer 2 matching, however there's an outstanding issue. I also have to account for ARP, otherwise these hosts won't be able to learn each other's MAC addresses. We call that ARP requests our broadcast messages. So these two flow entries won't work because they don't cover layer 2 broadcasts. ARP replies are unicast, so these rules actually will cover for ARP replies. So to match ARP requests, I'm using some new fields. DL_type equals hex 806. This is the ether type value for ARP. Also ARP code 1 is for ARP requests. So I use NW_proto equals 1, and that takes care of that. In the comments, I'll list the common DL type and NW proto fields. My action here is flood, just to make this easy for now. Flood means to send a packet out all ports except the one it arrived on, like normal switch flooding. Let's make sure this worked with ping all. And we can see H1 and H2 can reach one another, but no one can reach H3. This is expected since I didn't put in any flow entries to send packets to H3. If we do, break out of there. If we do dump flows on S1, we'll see our 3 rules and then we have hits to all 3 rules. Layer 3 matching. Now let's match on IP addresses at layer 3. I'll let all the hosts talk to one another in this example. Also, I'll do a packet modification. I'll give all packets coming from H3 a DSCP value of 46. So maybe I want to do this for quality of service to mark packets from H3 for expedited forwarding. Let's clean up our old flows, and now I'll add some layer 3 rules. So first I allow anything in 10.0.0.0/24 to talk to one another. I'm matching here with NW_SRC for source IP and NW_DST for destination IPs. The action is the normal action. I'm using DL_type equals hex 800, which corresponds to IP version 4. In the second rule, instead of saying DL type, I'm now showing the use of a keyword, IP. You can use keywords instead of trying to remember DL types and NW proto numbers. Again, I'll list many of these in the comments section. Now a critical point here. When defining matches at layer 3 and layer 4, you have to follow what the OVS OFKettle man page calls normal form. What that means: if you're trying to match on a layer 3 field, you are required to specify the DL type, like hex 800 in this example, or use an appropriate keyword like the IP keyword. If you leave DL type out, OVS will ignore your specification of network source and network destination, and it turns those fields into wildcard or match any. So again, when you're calling out layer 3 fields, you have to specify the DL type. Also, when you're matching on layer 4 fields like TCP or UDP ports, you have to specify both the DL type as well as NW_proto, which we saw previously and we will see again shortly. If you don't do this, if you don't follow the quote normal form, you will not get the results you expect. Okay, back to my second flow here. I'm doing a modification now. I want any IP packets coming from 10.0.0.3 to get a DSCP value of decimal 46. The type of service, our TOS field, is 8 bits, but the first 2 bits are reserved for explicit congestion notification, or ECN. So I have to take the DSCP value I want of 46 and multiply that by 4 to get 184. With packet modifications, you have various options, like modifying MAC addresses, IP addresses, MPLS tags, or VLAN tags. In a video on using multiple tables, I will do some of those other types of packet modifications. Okay, let's allow ARP again, this time in a different way from the layer 2 matching example. Now I'm using the ARP keyword instead of DL type to make my life a little easier, and I'm saying specifically where to send ARP requests and replies. Look how I'm using NW_DST. Just like I did for IP packets, but now I use the ARP keyword. Whereas before IP meant destination IP, now since it said ARP, I'm talking about the layer 3 target for ARP requests, and the source of the request in ARP replies. So you can see I'm using the field NW_DST in a different context, that I think should give an idea about the normal form requirement I mentioned before, where you have to specify a DL type. Another interesting thing with my ARP rules above is I'm not flooding ARP requests. I'm telling switch S1 where to send each ARP request. Versus normal ARP, which is flooded out every port, this is pretty cool. Okay, a quick check. And we see ping all works fine. And if we do dump flows, we see hits to all of our flow entries. And just to prove my DSCP marking worked, here is a Wireshark capture. And we see packets have a DSCP set to 46. Layer 4 matching. Let's wrap up with some matches on layer 4. For this, I'm going to start a Python web server on H3 and then let H1 and H2 connect to H3 on port 80. Deleting all flows again, or flow entries rather. I'll start the web server on H3, and let's put in our rules. First I need ARP again, so for ARP a really easy flow entry this time. Just doing the normal ARP behavior because I don't want to focus on that here. Now the layer 4 matching. Here I'm saying IP again by using DL type hex 800. I also use NW_proto6, which corresponds to TCP. Also I have a new match field, TP_DST. That's for the transport layer destination port, which will be 80. Something interesting here, note I didn't call out any specific IP addresses, so actually I'm sending all port 80 traffic to port 3 regardless of the destination IP. In this scenario it doesn't make much sense, but imagine if you wanted to send a certain type of traffic through a firewall. Some kind of rule like this could accomplish that. So I still need to permit return traffic, so let's do that. Any IP packets from 10.0.0.3 will just take the normal action. Let's see this in action with h1 curl h3. And we see that works. Let's try h2 curl h3. And that looks good as well. That wraps up this video. I hope this was helpful to get acquainted with flow entries. If you want to see more content like this, please subscribe to my YouTube channel. Also, I'd love to hear from folks watching these videos. If you'd like to connect, you can reach me through LinkedIn at linkedin.com/in/David Mahler.